Okay, so good morning, everyone. I am Unai Munoz, a PhD student at the University of the Basque Country. Today I'm very excited to share with you my research project about ensemble learning. I have to say that this is my very first publication and also my first conference, so I'm very pleased to be here with you in this conference. Mm, okay, first of all, as we all know, an ensemble learning and image classification model typically involves classifying and seeing data based on its characteristics. And in this new study, we introduced a new approach that uses a combination of data augmentation and ensemble-based methods in order to enhance the performance of standard or conventional classification models. Our research experiment involves several crucial steps. To begin with, we generated a testing set by employing rotational augmentation techniques on the original set, and then we implemented ensemble learning algorithms to every augmented set by combining the outputs in order to get a symbol prediction for that augmented set and as a consequence for every particular original image. Using ensemble learning with more outputs can lead to improved performance compared to standard classification models, but it also brings increased complexity and longer training times. So, in future sections, we'll be analyzing this impact. The success of our approach directly depends on the improvement we achieve. If our results show better accuracy compared to standard classification models, it will suggest that the specific data augmentation and ensemble learning methods hold great promise for further research. On the other hand, if our results do not show much improvement, we will need to understand why and explore other possibilities for future research. During our experiment, we took great care in selecting the datasets for a comprehensive evaluation of the proposed approach. We chose three different datasets containing different characteristics and representing different domains. The first of them is the chess database that consists of six different classes, one for each piece used in this game. The main objective of the second database is the sport ball dataset, and an objective is to analyze or to classify the balls used in nine different sports, such as basketball, soccer, baseball, and so on. The last data set is the animal data set, consisting of three different classes, one for dogs, other for cats, and the last one for wild animals in general. In order to achieve acceptable results, the number of classes is not always an important factor to take into account, but the number of samples indeed is. The more samples used to train a model, the better future extraction will be performed. So at first, in the pre-processing phase, we try to select the same amount of samples in each class in order to get balanced data set and to ensure comprehensive evaluation and fairness. This value has been determined by counting the samples in the smallest class, and then this value has been decreased to the 80%, 50%, and the 30%. Applying this process, we try to generate more training and testing set and analyze the impact of this value on the model performance and to get a stronger assessment in the final section. To generate our testing set, we employed a series of transformation techniques on every image from the original data set. In this case, it's also the training set, and and this these transformation techniques allow us to create modified version of the original image by rotating the three image three times in an anti-clockwise direction and then flipping them together with the original one. This flipping process essentially produced a mirror image of the originals. During this transformation, we adjusted the position of every pixel according to the transformation, in this case the rotation, and some pixels fall outside some pixels. It's possible that some pixels fall outside the boundaries of the image, and also that comes from outside the canvas. So in this case, these missing values have been replaced with the background color, generally with the black color. In order to enhance the performance of our classification model, it is crucial to identify and then select the most relevant features for the dataset. The Waikato environment for knowledge analysis software provides a range of feature extraction methods, such as the filter methods, which allow us to pre-process the data based on the statistical properties and relationship with the class variable. The filter methods allow the model to extract numerical representation of the image characteristics, and such features include texture, color, shape, and intensity, for example. It's important to note that not all the extracted features are equally important or useful for our specific goal, and some of them may be noisy or can negatively impact on the model performance. During the training phase, several models have been constructed using K-fold cross validation with a K value equal to 10. So in this case, every data set have been divided in 10 size, so in 10 sets of equal size. 9 of them have been used to train a model, and it has been tested on the remaining one. To provide an overall estimate of performance, the metrics obtained from each fold have been average. So we can say that the cross-validation provides a more accurate estimate of a model performance than just testing it on a single test of data. So in this case, the this approach is new approach. Instead of applying the ensemble methods to the results obtained from the different classifiers. In this case, five of them have been used, and the k nearest neighborhood with a k value equal to 5, the naive bias algorithm, the J48 algorithm, random forest, and SMO algorithm. So instead of applying the ensemble learning to the results obtained from these results, this approach employs two different voting systems. In this case, the hard voting and the soft voting to each set acquired from the augmentation techniques. And as a consequence, when analyzing the 8 augmented instances, the more accurate or the more representative one has been generated or decided, and this will be the final output or the final prediction and the standard classification accuracy will use to get the results. The process of hard voting involves each model in the ensemble, in this case every augmented set, to get an individual prediction for the set. It relies on the most frequent prediction made by the models. So essentially, the final prediction is the one that has the most votes from that individual uh, set. In contrast, soft voting is a more refined approach that takes into account the probability distribution generated by the model, rather than simply counting the number of votes for each prediction. This voting scheme computes the average probability and gets the highest one will represent this particular or every particular set subset. Here we have in the screen two different sets, augmented sets with their outputs regarding the hard boarding schemes. 5 instances have been generated or have been selected with the respective output. We can say that three of them are classified as the class number 1, 4 of them as class number 2, and only one as class number 1. So computing this information, we are sure, or the model is sure that that this particular set, and as a consequence, the ordinal image belongs to the class number 2. Regarding the software schemes, there are the instances and the class probability distribution. For example, for the instance number 2, the model is 62% confident that this instance belongs to the class number 1, 25% that belongs to the class number 2, and 13 to the class number 3. Computing all this distribution by the categories, in a general way, the model is 64% confident that the whole set belongs to the class number 1, and as a consequence, the original image. And being this the highest value will be the most accurate probability distribution. Here we have the results obtained from the different data sets across all the classifiers and descriptors. The standard classification accuracy is represented by the gray color, and the voting and the results obtained from the voting schemes are represented by the blue for the soft voting and orange for the hard voting system. In a general way, we are sure that the standard classification accuracy is enhanced by both soft voting and hard voting subvoting system. The most remarkable results are the ones obtained from sorry, from the random forest classifiers across the 4 descriptors. In some cases, they reach almost the 90% of accuracy. For example, the random forest classifier analyzing the Foxy descriptor, as well as the random forest with the age descriptor. There are some other cases, for example, the knife bias classifier analyzing the age descriptor, that for the hard voting, it's the improvement. It's positive, but it's not so notable compared to the standard classification accuracy and also with the soft voting accuracy. The best result that the soft voting accuracy has obtained is with the random forest classifier in the Foxy descriptor, and in the rest, the improvement it's not so good. Regarding the sport ball data sets, first of all, we can say that the results are much lower uh, for the three parameters. But also the random forest classifier has achieved the better results in the also in the four descriptors. There are some cases, for example, the knife bias classifier with the Foxy descriptor, where the standard classification accuracy has achieved better results than the hard voting system. In a general way, the knife bias algorithms do not perform well, so it's not. If we are doing some other experiments, this will not be included so more. For the last data set, the animal data set, the results are in general much higher than the compared to the previous one. The results for the soft boarding and hard boarding schemes are very good. In the first approximation, we can say that they are they are very good and they achieve very good accuracy, but compared to the standard classification accuracy, the improvement it's so notable, and that was the main goal or the main objective of the approach. Here, for example, the random forest classifier analyzing the Foxy descriptor also achieves the better results. So we propose for further research to analyze this classifier, as in the three of cases have performed very well. Although our experiment have achieved the main goal of the proposal, we also think that there is a need for further research in this area. In a fourth approximation, it is crucial to analyze the need for adjusting the number of rotation applied in the data augmentation phase, and this will lead to create less or more modified versions than the ensemble algorithm will use, and as a consequence, the cost or computational cost will be also reduced or increased. It's very important, or this value has to be carefully chosen, as too many of them can lead to a lack of diversity, and many can introduce noise on a negative impact on the model performance. That's why it's very important to strike a balance between the improvement and the additional computational resources that the models need to be implemented. However, when using data augmentation techniques, some of the rotation may not be as representative as others. So instead of selecting the same set of rotation for every class, a previous study is proposed based on the number of rotation that I have mentioned before, and consequently, we would like to set this rotation based on the characteristic of the dataset, the class variable, the categories to be analyzed, and some other similar factors. Finally, and as I said before, rotation processes tend to cause some of the pixels fall outside the image boundary, and this value has been, so this problem has been fulfilled by replacing this with a background color. But for further research, interpolation techniques are proposed where the missing values are proposed to be replaced or calculated based on the values of the nearby pixels. The approach of applying bounding schemes to every set of 8 instances is a promising new technique that has improved the precision of image analysis. In general, both hard and soft bounding schemes have enhanced the results obtained for the standard classification models, reaching around 10 and 20% of improvement. It's true that while there have been cases where the standard classification accuracy have achieved higher results, there are also some cases where, for example, the harboring scheme has achieved a 50% of improvement, which is completely insane. However, it is essential to note that this approach may introduce some noise or some degree of complexity between the both sets. We know that the ensemble learning algorithms combined with the data augmentation have provided a wide range of benefits, but there are also some potential drawbacks that we might take into account. And the most remarkable or the most important has to do with the additional complexity that this approach creates. So so as I said before, in the according to the dependencies, as all the data and the image of the testing sets are created from the training sets, it's proposed to apply some other transformations, different transformation, and also to delete the original image from the from the augmented sets, not to get the same image in both sets. It's important to ensure that the data used to train the model is representative of the real world scenario. So if the data is imbalanced, meaning that one class is significantly more represented, the model may learn to predict the minority class more accurately, and this is not a very a very important benefit to take into account. Creating multiple data sets with varying sample sizes have helped to improve the average accuracy of the voting schemes. And this approach, so we are sure that this approach helps to identify the optimal number of samples required for every particular objective that we may set before starting the experiments. Additionally, it's also true that it provides insights into how the model performs under different sample size condition as the best across all the options have been chosen, it could be a reason of why the results always shows improvement in the majority of cases. So this has been all. I hope you like it. Thank you for listening, and I will be very pleased to answer every doubt or every question that you may do. Thank you.